Welcome to the MOOCs course on object oriented analysis and design. This is module 1. Here we will start by setting the background and creating the motivation for why is it required to study, understand object orientation. How does it play with analysis of real life problems and how it can be effectively used in design of complex software. Certainly, you all are familiar with object oriented programming, at least I assume that you know glimpses of that. You are aware that C++ or Java are some of the most popular object oriented programming languages. Now, the fact of the matter is that while you design, implement and maintain a complex software, certainly using an object oriented programming language turns out to be of great help, but merely the use of a object oriented programming language, that a programming language which supports definition, creation, management, destruction of objects, merely the use of that language as a programming vehicle does not solve all the issues of software system. And in reality, much of the problems that software systems encounter or the developers and as well as the users of the software systems encounter are not just limited to the programming code. Several actually significant part of the problems start at the specification of the problem itself, where the user talks to the developer and wants to express that this is what I want as a software. Now, in some cases users will directly do that. If you are have an enterprise and you are trying to get a system created by a software vendor, say to manage your employees, to manage the leaves that your employees take, you will directly talk to the vendor and get a system created for your organizational use. Or it could be that it is a generic software product, where several independent unknown users have talked to several parts of the developers to express their requirement, and all those requirements had been canned into a complete set, a consistent set to develop the product. An example would be Microsoft Word, Excel, this Office suite and mail clients, browsers. They have not been developed for any specific needs of any specific organization or individual. They have been created for generic use by a large number of individuals, groups and organizations, and therefore, we call them the products. Irrespective of which kind of software system we talk about, the specification, design, analysis and finally, implementation, maintenance, preservation are all critical issues that need to be effectively handled, particularly for a industrial strength large scale software. So, you would be familiar that this whole exercise is christened in the name of software engineering. Like civil engineers construct buildings, mechanical engineers construct automobiles, machines, electrical engineers construct power plants, air conditioners, fans. Software engineers are supposed to build software, and that discipline is known as software engineering. So, to understand the requirements, or rather more the motivation of why we need to engage in object oriented analysis and design, we will start by taking a brief look into what are the challenges that software engineering or software engineers face. That will be the mainstay of our current module. So, to specify the specific objectives would be to understand why software is still developed and not constructed. Please note these two words development and construction, if you delve into any field of engineering other than software, then you will typically find that the word used at the to define the activity, to define the product is called construction. Buildings are constructed, power plants are constructed, but software is typically developed, it is not constructed. So, we will take a little bit of round in terms of why this difference in semantics. We will try to understand why software projects fail and take a glimpse into some of the remedial measures. And finally, we will end the module with a KYC, that is know your course, that is what are we going to cover in this whole. The outline would be, is software, what is software engineering, or rather is software really engineering, and why projects fail, and so on. And the convention that we will typically follow in all the modules is during the presentation you will be able to see the outline of the module on the left hand side of every slide, and the current subsection in the outline that is being discussed in a given slide will be highlighted on the left. So, this is the outline that you will have. So, now let us look at software engineering. So, the order of the day is to refer to the activity of software development as software engineering. I start by raising a question, that is it fair to really proclaim that we are doing software engineering. If we are doing software engineering, then we must be able to construct software as civil engineers build bridges. So, what is engineering? Engineering in very simple terms can be looked at from different angles, but the core concept is it is a skill of construction. Engineering also deals with the ability to manage complexity. If you, what is the difference between science, theory and engineering? The science tells us the natural laws, principles, mathematics that govern how systems will behave. We turn them into engineering when we add utility to what we do. One or more people, one or more organizations, nations, groups get benefited, and the second very important factor is we create something which did not exist. And in the whole process, we really need to learn engineering because there is a complexity to handle. If things are small, simple, then you do not need to be an engineer. You can, if you just want to analyze as you throw a ball and want to hit a target, what is the force with which you will throw the ball and hit that target, you can do that from your study of physics by using Newton's laws of motion. But when you want to do that with by firing a missile which has to go over 5,000 kilometers and still hit a building at the right point, you need to do engineering. Both are actually hitting a target over a distance, but what is different in case of a missile is the complexity is very different. So, when we talk about engineering, we basically talk about how to manage complexity, and that the core skill of an engineer is to learn how to, what is the complexity and how to handle that. So, just to take a glimpse, we will take a quick tour. This is more of a storytelling, a quick tour into some of the common fields of engineering and see how they have evolved. So, we will start with 4 different domains: the bridges, the surgery, aeroplanes and certainly software. So, if we look into bridges, this is one of the earliest constructions that the human civilization had to do. From time immemorial, we have been constructing bridges, first with wood, stone, then iron, steel, glass, concrete bridges and so on. And by now, if we are given to construct a bridge, then we do not accept this outcome that the bridge may fall, that the construction may not succeed. If I construct a flyover, I would not expect the flyover to fall over. Let us not talk about incidents in Delhi and Kolkata that we have seen in last couple of years. That is false in engineering, but the civil engineering knowledge guarantees that the bridges will not fall. So, constructing a bridge is different from innovating a bridge. We will say we are innovating on a bridge if we are experimenting with a new material. We have seen bridges with this iron, steel, concrete, but then if you look up the Google for Grand Canyon, you will find bridges which are completely in glass. So, when civil engineers sit down and find out how a bridge can be constructed completely with glass and experimenting, or they are innovating a bridge. But when they are actual engineers and constructing a bridge, then they are working with established metrics, standards, proven processes, so that there is no innovation particularly and the process must succeed. The same story will reveal itself in other fields. Just consider medical surgery. Health naturally has been an issue of concern again from time immemorial, and as is documented that surgery and the act of barbers were considered equivalent prior to 18th century. You had to cut the human body and do something. It was declared quackery by 1900, but people slowly, the doctors or surgeons started perfecting on the surgery, but most patients did not survive because of the ensuing infection. So, we learned how to manage infection in the late 1800s. Now, if you look into the way the surgery is done, every surgery follows a strict protocol. This protocol is nationally and internationally established, proven, and the doctor and the team has to specifically follow that protocol to ensure that the surgery succeeds, the infection is not propagated to the patient and so on, and that is the reason that surgery today has become so successful. So, that is also a kind of engineering that we see, and you can see that the success rate is quite high, and without that, of course, we would be very scared to go to the surgeons. A third domain is airplanes. Many of us certainly love flying, and again the attempt started at around 400 BC with Chinese trying to flying kite and aspiring that humans could also fly. For centuries, people have tried to fly as birds with disastrous effects. Many people have lost their lives. There have been different means of flying, steam powered, hot air, gliding for single man, engine powered and so on, till about little over 100 years back, the Wright brothers finally made the today's prototype of airplanes and they could fly. Again, if you look at how the airplanes are manufactured, how they are flown, they are strictly regulated, governed by proven practices, standards, and if those standards are not adhered to, then the airplane will not, or the aircraft will not be allowed to fly, the pilot will not be able to take the seat and so on. And that gives us the comfort, the guarantee that if I fly in an aircraft, then I will reach the destination safely. So, in all of these fields, the underlying factor is the confidence or the surety or the guarantee of success is very, very, very high. And often when things go wrong, when things fail, they fail either because some human being has made a mistake, or several human beings have made some mistake, or there is some intentional wrongdoing. In contrast, let us look at software development. I love to call it the art of problem solving. The vision for computing, mechanical computing, automated computing started in early 1800 with Babbage's, Charles Babbage and Ada and so on, but incidentally there was not much development for over 100 years after that. The first significant step towards software, algorithms and software systems happened in the 1930s with the two seminal work, one by Kurt Gödel's incompleteness theorem and Alan Turing's Turing machine. Many of you may have heard of these. So, if we look at, then software is not even 100 years old. So, it's compared to other fields of engineering, it's very, very nascent, very, very new, and therefore, it has not got the time to really prove its processes, set up its standards and make sure that the success will always be at the end of the road. Of course, we see a lot of development happening, very fast developments, machines are expanding, they are getting faster, more powerful, lot of machines, yet is the software delivered successfully? We all understand that it is not. And let me, for the sake of being formal in this course, define what I mean by a successful delivery of a software. It means primarily 4 factors: that the project is completed on time as was planned, there is no extension of the project, it is completed within budget, that is there is no overshoot of funds, all features that were promised are complete. It is not that I do it on time and within budget and implement only 50% of the functionality that I wanted. And finally, it must be a working software, that is it should be failure free, fault free. Now, in this background, if we look at some of the recent studies, these I have picked up from the sources governance. These are 5 years to absolutely recent study, which show that more than 30% of the software projects fail, and this statistics is also taken for really large projects. If you take into medium sized projects, the success rate would be even lower. So, that is quite alarming, and this is another data which is very recent, couple of days back, which show that over the last decade 2006 to 2016, what are the different large number of large projects that have failed. So, here these bubbles, the circles show the kind of budget that that particular software had. So, the selected one that you can see here, this one is actually a 12.7 billion pound project, which had to be terminated by the UK government little around the middle of 2011. And these show that there is a continuous, I mean, irrespective of which region of the world you are talking of, there are a series of large to very large to huge software projects which are failing, causing several damages to property, the loss of money and effort and resources. So, that is a basic alarm point. So, we just try to, we will talk about this a lot more, but here at the in this introductory part, I will just quickly try to highlight why software projects fail. There can be one line answer: the complexity is the culprit. There is complexity of several dimensions in software development. So, some of them you can very quickly understand is the change of requirement. When you start developing a software, you are told something, and then as you go through the development, the customer would repeatedly come back to you and say that I want something different. Now, is it that the customer is not a smart person? Is it that the customer is not being truthful to you? No, please do not misunderstand the customer. The customer is changing the requirement because the customer originally did not know what she wanted. She had only had a vague idea, and as you start building the software, you show the prototype, you show the design, you show the first alpha version, the customer gets more and more ideas. The business environments change, conditions change, processes are re-engineered. So, one complexity, big part of complexity come from the change of requirements. A different complexity come from change from technology. Your software works on systems, works on hardware, works on network components, works on different operating systems, third party protocols and so on. Over the period of your development, if it is 1 year, 2 years, the target system that you had started working with, that system itself evolves and a new system is around. When you started, it was Windows 8.1. By the time you are in the middle of the project, it is Windows 10. Things have changed. The things may change in terms of hardware. So, being able to adapt to those adds a new complexity to the whole process. And there is a severe complexity from people. Unlike most other fields of engineering, where the process of construction itself is significantly automated. Here in software, the process of construction has automation aid, but it is finally people who develop software, who write the code. So, interaction of people, as you will always understand, are complex. Two people have certain kind of interaction. When you put 4 people, you get 4C2, 4 choose 2 kind of interactions, and you have more and more people, more and more groups, more and more organizations, more and more distributed development teams across geographies and so on. Interactions get really complex, and people are one factor in the whole software industry which have an unpredictable behavior. You, me, everybody have certain uncertainty in terms of how we will behave today and how we will behave tomorrow. We say, I mean, I am not in a right mood, I may not be in the 100% fitness and so on. So, complexities in software development come from all of these different dimensions. This is not an exhaustive list. We will talk a little bit more about software complexity in the next module, but this is just to give you a glimpse in terms of why software projects fail, and we will have to live with that. So, the question is, the moot question is software engineering is like manufacturing, where you have proven processes and you just make a cell phone, or it is like designing a manufacturing plant or like making a cell phone. So, these are two different aspects. One is when somebody started deciding that or dreaming that there should be cellular phones which should be usable anywhere, to the point when today you start making Samsung Galaxy phones and iPhones and so on, these two scenarios are different. And for your statistics, it took about 37 years to make commercial cell phones. So, now the manufacturing process is predictive, it must be predictive, you must be able to measure and control quality as well as quantity. But designing the manufacturing plant is a creative, innovative process. Interestingly, most software development continues to be innovative process rather than predictive manufacturing. So, that is what makes it difficult to view software building, software development as a construction process, because it does not have the reliability, predictivity of manufacturing, of construction. It requires great deal of innovation, interaction, communication, and all those factors impact the success of the projects. So, we have a long way to go from the status of software development to the status of software construction. We look forward to a day when, like civil engineers, electrical engineers, we will be able to say that we have constructed a software, and if we have constructed a software, it will work. The process will be predictable, quality will be predictable, quantum will be predictable, cost will be predictable, and we will adhere to all of that. The present state of the art say that this transition needs structured analysis, modeling, design, and implementation. We will slowly understand through this course what these terms mean in depth, and it also needs that we can adhere to good practices. If you look into any of the streams of engineering, there is a large volume of handbooks and standard data and practices which the engineers must follow. That is the code of conduct. I mean, you just cannot deviate from that. Software engineers are still not up to it. So, we are still struggling even to follow the coding guidelines in programs. So, the fact of the matter is that object oriented analysis and design is a precursor to achieving both these major tasks, which will take us forward somewhat closer to software construction than the state of development that we are in. And that is the main motivation of discussing this course. So, before I close this module, let us quickly take a look into knowing your course, the course outline. We will talk about software complexity, understanding the challenges that OOAD can address. We will discuss about object models, how to define the primitives of the object oriented paradigm. We will talk about classes and objects in terms of bringing in the broader perspective of modeling, and we will talk about how, with all these definition and background of theory, we will actually do hands on exercise and give you concrete principles in terms of how you can really identify what are the approaches to identify objects and how to analyze them, how to design based on them. And in this whole process, we will start using a language, a graphical language, which is kind of a de facto standard to express object oriented systems today, known as the unified modeling language. And for 3 weeks, we will learn this language, we will take several examples to model in that language, and we will show you exactly how to use this, how to talk in the lingua franca of object oriented community. Finally, before we end, we will try to discuss and make you work through some of the case studies, where OAD will be applied to different contexts. This is the textbooks. There are several books in object oriented analysis, design, programming, UML and so on. Just to keep you focused, and certainly I would like to recommend you to follow this book as a textbook. This is certainly, in whatever I have seen, this is the best book on this topic, written by several stalwarts, spearheaded by Grady Booch, who is a Turing awardee, and he is with IBM now. And please follow this book. This has most of the material that we will discuss will be borrowed from this book, and also the whole discussion of UML has a good summary in this book, and if you follow this, I am sure you will find this course quite easy to go. These are some of the examples that we will try to follow. All through this course, or the major part of the course, we will use a running example. So, while we discuss about different points, we will take glimpses from one running example about a leaf management system of an organization. So, very soon we will introduce you to the general notion of this system, what does an organization think about leaf management, what is required, and then we will repeatedly use that. Besides that, we will have examples from Gooch's book. We will have a separate running example in the assignments that you will do. That is an assignment management system, where the assignments that students do are managed through that system. Besides, we will have Gooch's examples from Gooch's book. And for complete workout, we will have couple of different example systems of postal management, story management in a newspaper house, car management for a rental car company, and some of the OAD examples. Here are I am your instructor, as you know. So, my contact is given here, and I am assisted by 3 TAs, Tanni Mollik, Srijani Mojumdar and Himadri Bhuiya. So, they will be accessible on these emails and phone numbers in case you need. So, we will summarize that software engineering is closer to development than to construction. This is what we have seen through the simple discussion that we have had. We have also observed that software projects fail due to complexity, due to regular need of change, and we have noted, and this is what we will demonstrate through the course, that OAD can take software from development to construction over a period of time.